All right, so at 25 degrees Celsius, water does something. It does something that you wouldn't initially expect it to do, per se, but if you have water at that temperature as a liquid, because it's pure water, there's a very tiny proportion of it that will break apart into H plus and OH minus. Now, we usually talk about things in terms of H3O plus, and to make this turn out to be an H3O plus, we just use two waters. They're reacting with each other, and it becomes H3O plus. So remember there, you can interchange where they're talking about the H plus or the H3O plus. Many people don't even make this distinction. But in either case, what they are is they are just dissolved ions, but there's only a tiny percentage of them that do this. The actual percentage, it's called the KW. It's the dissociation of water. The percentage that split apart is 1 times 10 to the minus 14th. And you're probably thinking, what on earth? That's such a tiny number. That's like 13 zeros in that. Why do we care about something that has that 13 zeros? Okay, so this is why we care, is because something else can react with water and can generate extras of these. Also, we had to base a scale of acidity on something, and using water because it's so prevalent was a very good choice. So we judge how acidic or basic that something is based just on the equilibrium and the dissociation of this. So what we know, if we were going to write this expression, is that this value is going to be equal to H3O plus and OH minus. Because this is a liquid, you don't put it in. So if we were going to go ahead and write the ice chart for this one out, and this works for both of them, this one's won't matter, whatever you put in there, because it's a liquid. Initially, you don't have any of it. You gain X, and so that means at equilibrium, you have X and you have X. Weird, right? So 1 times 10 to the minus 14th is equal to X squared. Now, you can throw this calculator in if you don't believe me, but when you take the square root of 1, it becomes 1. And when you take the square root of 10 to the minus 14, it's like saying that times 1/2. You end up with 10 to the negative 7 is equal to X. So any water at 25 degrees Celsius will have this number of H3O pluses floating around and that number of OH minuses floating around at 25. And so still, though, that's a really small number, right? Well, if we have the same exact amount, then what we can say is that it's neutral. Like it's just a neutral amount because there's always one OH for every H3O plus, and you aren't going to say something is acidic or not. If you have more H3O, let's say you have like 1.3 times 10 to the minus third, because something has reacted with water and generated more of these than water naturally has. Well, then how do you talk about something having that much H3O plus versus having that much versus something having, 1 times 10 to the minus 11th H3O plus? Like, how do you talk about that without losing your mind, talking about 2.5 times 10 to the minus 3 and 6.8 times 10 to the minus 8th? There's a point at which it just makes it hard to really recognize what you're talking about. When that happens in chemistry, sometimes what we do, in addition to scientific notation, is we jump to start talking about just the exponents. And that's what we did in this case. So anytime you take the log of a number, it's kind of like let you talk about something in terms of its exponent. If you take the negative log of something that has that kind of an exponent, it'll give you a number like 3. If you take the negative log of 1 times 10 to the minus 7, it gives you a number like 7. Notice that I'm getting these numbers. And if you take the negative log of something that's 1 times 10 to the minus 11th, well, then it gives you a value of 11. So what they decided was, let's not worry about talking about things with these strange magnitudes that are very, very, very tiny and can be cumbersome to talk about. Why don't we just introduce the concept of, hey, we're talking about the exponents and we're just talking about pH. And so that's what we did. We talked about pH, and pH is like saying we're just talking about things in terms of its exponent. So from all of this information and from this right here, what they said was, okay, let's come up with a pH scale so that we can know what pH really means. We know that when everything is neutral, 1 times 10 to the minus 7th, the negative log of that is 7. That's when everything is neutral in the water. But if we put something in the water that reacts with the water that makes like extra H3O plus, well, what does that mean? Well, if you've got extra H3O plus, that means it's more acidic. And then let's say we act with the water and we make something that makes a lot of OH in it. Well, then we're going to have a really tiny percentage of HCO plus, H3O plus, and that one's going to have a number like 13. So from all of this information, knowing where this dissociates, knowing where they are equal, scientists came up with a pH scale. And on the pH scale, they set up the pH. Again, we're really talking about the exponents, but everyone skips that whole step. And it's really talking about the concentration of OH. And we say that 0 is where you are very, very acidic, and that 14 is where you are very, very basic. All this corresponds to you is that you need to know the ends of the pH scale. You need to know this formula and know that this formula can be used not just for water, but this portion of the formula can be used to convert between H3O plus or OH minus concentration.